And now our next presenter is engineer Syed Abbas. He will present physically here, and the title is Physical Modeling of Mahman Dam Spillway for Performance Evaluation of Aerators.
Dr. Ajay, can you kindly unshare the screen? Turn off the share screen mode. Dr. Ajay, can you hear me?
Bismillahirrahmanirrahim. Wa huwa al-aliyul azim. All attendees, my seniors and seasoned engineer colleagues, professionals, all online attendees, Assalamu alaikum. Today I will be presenting my research work based on hydraulic performance evaluation of multiple aerators, which is a case study of Mohammed Dam spillway. This research work is part of funding from HEC under National Research Program for Universities and also part of the PhD research. In this presentation, we will be focusing on the research part, and the research part basically focuses on the physical model study that we have done to evaluate and observe different parameters for our further use in research. The overall research purpose was to evaluate the spacing of multiple aerators along steep spillway chutes for high-head dams and spillways. First, I'll introduce my first three objectives. The first objective relates to the physical model study, where we had to observe different parameters for validation of our CFD model. The second objective dealt with the different simulations that we will perform on our CFD model. And finally, the last objective on the development of a relation, on how to develop a relationship. As I said earlier, this presentation will focus primarily on the physical model study part of our research work for achievement of objective number 1. Gentlemen, this is an overview of the overall research work that I had just verbally explained to you. The first part, if you see, is objective number 1 over here, where we have to do the physical model study. Just for the students that are over here from bachelor's, or an overview for the faculty members, we will perform physical model studies, take data for our numerical model development, perform numerical simulations, and use these model simulations for different analysis to develop an empirical relationship, and finally conclude it with our research work. Now, for physical model study, we had developed a research methodology, work methodology on how we need to observe these parameters that we shall be using for our research. First of all, we had to take approvals from WAPDA. Now, the model we are using is basically under the ownership of Water and Power Development Authority, WAPDA. We collected the data with their approval, and an existing model was available for us to work on. So we had an inspection done at the model to see that out in the open when a model has been developed, has it gone any harsh effects in the weather conditions? Is it possible for us to use that model for our research? Does it fully comply with our requirements? Based on that, we carried out some inspections, calibrated the model. Calibration in this case was verification of whether the results we are taking from the model are correct and for proper use in our research. Then we performed different simulations, different scenarios that we observed at the physical model. These were for both gated and free flows. And then finally, we came to the activities where we extracted the results and used them further. Basic work is on, of course, the Mohammed Dam spillway. So the basic parameters of the dam and spillway you can see over here. The dam type is a CFRD, having a height of about 213 meters. The spillway is a free fall overflow spillway where an ogee crest is provided with radial gate arrangements. There are 7 bays in all, each converging to the stilling basins. Now there are 2 stilling basins provided in this case. Since the drop is large, the energy dissipation has been made in 2 different steps, and 5 aerators have been provided in the design. This is the picture of our physical model. You can see the chute, the aerators over here in the first step, the stilling basin, the next chute, and then over here our stilling basin. The model was developed by Irrigation Research Institute under WAPDA Model Study Cell, and the data and guidance and supervision was carried out by Mohammed consultants during 2012 to 2017. The first part of the model, like we explained, was related to the inspection and verification. In inspection and verification, we, like I said earlier, checked whether the model is fully compatible with our requirements. There is no information model structure. The results are reliable to be used in our study. And then the gated and free flow scenarios were tested. During physical model study, we observed 3 parameters for model verification. They included the spillway water surface profile, flow velocities, and aerator cavity lengths. These are results of our verification. You can see that we plotted both the data initially taken by, we took 2 discharges. Discharges taken by Mohammed Dam consultants during 2012 to 17. And then we re-observed data back in 2021 and then compared both results to see whether the model is fully in workable condition, and we found that to be correct. You can see that the water surface profiles and the velocity profiles nearly match with a difference less than 5%, which meets our requirements. Also, the aerator cavity lengths and the differences for the observed and the previous cavity lengths was within 5%. Now, the physical model study or the testing that we carried out. We developed 5 scenarios for our 2 scenarios were for gated flows or low flows, whereas 3 scenarios were for high flows. This is almost equal to the design discharge of Mohammed Dam spillway against a PMF return period flood. The parameters that we observed during physical model study were water surface profile, flow velocity, cavity lengths, manometric pressures, and air velocity at intakes. Now, each of these parameters has its own significance in design when we carry out design, like our previous presenters also explained various challenges. Each of these parameters needs to be studied very carefully during design. When we perform physical model studies, it is essential to take the information correctly and then use it in design so that we can fix the spillway geometry, its shape properly. The data primarily required was the tailwater rating curves apart from geometry, and then the rating curve of the spillway. So we took our reservoir levels and tailwater levels from the data that we had acquired from Mohammed Dam consultants and WAPDA. This is for gated flow conditions. And then for free flow conditions, where we tested 14,000 to 22,500 cubic discharge at the model. We performed different tests. One of the parameters that we observed was water surface profile. You can see over here, the water surface profile. This is along the ogee chute that goes down to the chute. Over here is the chute. You do see rooster tails, the jump that comes right after the piers. And then this is our first aerator over here, which we call aerator A1 in this area. This shows the overall water surface profile that we had observed during our physical model study. Now, in this profile, please do observe that this also shows the L section of our spillway. This is the first ogee. Drops down, we have a straight platform with the first aerator coming right at the curvature. From this aerator, air is introduced into our profile through the lower nave, goes down to the second aerator, and then into the stilling basin. The stilling basin has been equipped with baffle piers and enshoots with a secondary weir or an ogee crest at the downstream, which raises tailwater for proper energy dissipation in this area. Along the second chute, you see three aerators, A3, A4, and A5. Now, this is again a steep chute with a considerable drop. So we needed these aerators to ensure that there is cavitation-free operation of the spillway. And when our flow reaches down to the stilling basin, there are minimal chances of cavitation damage. Here we have our first aerator. Please observe the jet and cavity length from the top right is just up this aerator. This is the point of the that we are. Now, this is the second cavity, which we see pushing the tailwater flow backward, and we have a prominent cavity. The energy dissipation within the stilling basin, you do see bubbles over here. It's not very clear, but still, you do see bubbles over here. Bubbles represent the presence of air in this physical phenomena. So this is the second chute. Flows going down our third aerator, the cavity length. This is again our fourth aerator. And then finally, the last aerator over here. You do see air shafts over here. This is an air shaft here, and then another one over here. So ample aeration has been provided to ensure cavitation-free operation. We observe water levels through these gauges that we have pasted over here along the spillway. This whitish color you see on the aerator, this is the cavity length, the jump length that is formed at the aerator ramp, and then the point of separation where it takes the jump, and then the point of reattachment. In between these 2 points is the cavity. The cavity sucks air from the intakes. One intake is over here, and the other one is on the other side. So air enters through these intakes and is sucked in through the lower nape of the spillway or of this cavity length. And then aerated flow goes down to the next aerator. Further aeration takes place at these points. And then another aerated flow goes down to the stilling basin. Cavity lengths. These are the cavity lengths that we had measured for one particular scenario of ours. At the aerator A1, we see 33 meters of length, and then 17, 16, and almost 15 meters of cavity length. This is how a cavity length looks like, what we also saw in our previous video. You see that this is the point of separation, the cavity length, and the point of reattachment. We measured it using a simple meter rod and physically measured all cavity lengths. At the last aerator, it was not physically possible for us to measure, so we shall be doing that on our numerical model. Now, the performance of an aerator. A good aerator provides you with the right amount of air that you need to prevent cavitation. In this short video, you will see how our aerator is performing to the suction of air. When a ramp is provided, it will provide a jump to the incoming flow. Now, in this case, we see the air vents are clogged by these two persons over here. And only the effect of ramp is what you can see over here, how the flow takes the jump and lands on the downstream side. It takes the jump here and lands on the downstream side over here, and you see this cavity length. How this cavity length expands when air is introduced into it. This is what we can see over here.
Mr. Abbas, try to finish within 5 minutes.
It's closed. Now they opened it and please see the effect. The jump length considerably increased. This is the introduction of air. The aerator is performing well. It is taking air, and we can see that physically over here. This was our limitation. So due to high tailwater at the down, exact cavity length at the downstream at aerator 5. Manometric pressures. Now, cavitation, like also explained in previous presentations, is when negative pressures are developed at the surface. Small bubbles are generated that collapse and create shock waves and microjets that affect the concrete surface and cause pitting. So it is essential to measure pressures along the crest or along the chute of the spillway so that you can calculate or estimate what cavitation potential does your discharge hold for a particular design. For that matter, we performed manometric observations along the spillway using different piezometer points along the complete length of the spillway. These are some of our results. You do see negative values over here. The negative values report are inside the aerator. That means that there is a negative pressure being taken in. In addition to the manometric pressures, we had velocities measurement. Now in velocity measurement, this is the spillway crest and the reservoir. Although this slide is not very clear, but I'll try to explain it. Here we have our first aerator, aerator A1, and then the second aerator, aerator A2, A3, 4, and 5. Please observe the velocity values. For cavitation to occur, we have three main parameters to consider. The flow velocity, which if increases more than 30 meter per second can cause creation. Cavitation index, which falls below 0.2 may result in cavitation. And then the Froude number, which if increases above 6 to 6.5 may result in cavitation. So all these parameters need to be studied in a conjunction during a hydraulic design of a spillway. In this case, our velocity limits show that velocity near our aerators is around 27-26 meter per second. So the first aerator has been provided at location before the velocity crosses the velocity threshold of 30 meter per second. And then aeration has been provided and negative pressures can be avoided in the downstream area. You do see velocity increasing at the aerator, going beyond 30 meter per second, but this does not mean that cavitation will take place. Why? Because over here in this area, velocity values are high, but the negative pressures have been controlled due to introduction of air at the previous aerator. When we feel the requirement that cavitation index is falling below or Froude number is increasing, we provide a secondary aerator. This aerator will further provide sufficient air so that cavitation may not take place at the downstream energy dissipation devices within the stilling basin. The same is the concept over here in the lower stilling basin or the lower chute of the spillway. The same what I had explained, these are our results showing the same velocity values. A fluid. So you see high rate of bubbles over here in this area, which we see escaping at the surface. So air is introduced in our flow, but as it moves down, we also see that air is moving up and this is escaping the surface. So we do need aerators at the downstream and they have been provided. At the end, what was the intended use of our study and the parameters that we had observed? Like I said earlier, this research actually for our objective number 2, which is the numerical simulations, we have developed a numerical model, which is under process of validation. You see the model over here also. All image of our model that we had developed. The video is not playing actually, so the conclusions, we performed physical model studies, observed various parameters. The parameters will be used for the validation of our CFD model and used in further research work to develop a relationship for iterative spacing. And we intend to get that done much soon. And thank you very much. We acknowledge the efforts of all who have helped us out, especially Wabda Model Study Cell and Movement Dam Consultants. Thank you.
Thank you very much, Syed Ali Abbas, for enlightening us the role of multiple aerators through the physical modeling.